is a great pleasure to be able to introduce today's speaker. Marcelo Rubio did his PhD at the National University in Córdoba in Argentina. That's actually where I first met him. And also under the supervision of Oscar Reula. He continued to do postdoc at the Astronomical Observatory also in Córdoba in Argentina, and moved on to a postdoc at Brandon University in Canada. And currently he is a postdoc in SISSA in Trieste, in Italy, working with in the group of Federico Baraus. And so please.
Okay, thank you. So hello everyone. First of all, let me thank you for being here, and let me thank my friend Alex for this very nice invitation. We met again in Benasque. It was super nice to meet you again, and for this invitation. So thank you very much. So today I'm going to be talking about some the previous work I did in the past, even back to my PhD. I did my PhD in Argentina with Oscar Reula. We basically work among other topics. The main project was about relativistic hydrodynamics, in particular how to model the different ways to add dissipative effects to any effective theory for relativistic hydrodynamics in the context, for instance, of general relativity. So during my PhD, I could collaborate with many people, particularly with Luis Lerner from Perimeter Institute. I could visit the perimeter during my PhD, with Oscar Reula, with Ana Garcia Perciante from Mexico. And now I'm working with Pablo Montes. We are finishing our work on simulation of this, one of the theories we developed for conformal fluids. And Pablo is also a student of Oscar Reula. He's finishing his PhD. So the issue of modeling dissipative fluids in general relativity is still an open problem in the community, as you may know very well. So the idea of this talk is to review some previous attempts on modeling dissipative fluid theories. What are the problems that appear when modeling dissipative fluid theories, and some ongoing work on numerical and analytic aspects of this problem. So the main motivation I have for studying, for dedicating much of my time working on relativistic hydrodynamic is, as you know, if you want to model matter and energy theoretically in the context of theory for gravity, as for example general relativity, there are just a few ways to model and to have a theory for modeling matter and energy in GR. You can take, for example, the energy momentum tensor of Maxwell theory, if you want to consider a linear theory for electromagnetism describing electromagnetic fields in the concept of GR. You can also model with scalar fields, and with another possibility is to use, for example, the energy momentum tensor of a perfect fluid, which if you want to add matter in your simulation, the first attempt or the first thing you do or you think of considering is adding a fluid. So this is just one of just a few things we can do in order to include matter in general relativity. And in particular, relativistic hydro is a very nice framework for the thermodynamic description and dynamical evolution of matter and energy. We can use relativistic hydrodynamic both, for example, only in spatial relativity, in which we may have system moving with very high Lorentz factor, or also we can use the relativistic hydro equations if we want to couple or see the effects of the curvature of spacetime because of the presence of matter and energy. Another thing that I really find exciting on relativistic hydrodynamics is that the same theory can be applied in a very wide range of spatial scales, starting from microscopic physics, for example, in nuclear or particle physics. The most famous works in which relativistic hydrodynamics really has a very important role is on describing the heavy ion collisions in nuclear physics, but also it appears in larger contexts, spatial larger spatial scales, as for example in plasma physics, in astrophysics, or even in cosmology. So you can go from microscopics to very large scales of our universe. And the theory we use, or you can use in order to model the evolution of matter and energy, is exactly the same, is relativistic hydrodynamics. So in order to get started, let me just fix some ideas and some notation regarding how do I understand the fluid, what a fluid will be, at least in this talk. So if you want to describe a fluid, you can say, okay, we have a system of particles, so let's start from scratch, very shortly, but from scratch. So imagine that we have a system of n particles which are in a box. Those particles could have some weakly coupling, but we are not asking the system to be, for example, a lattice, like to be rigidly distributed in some lattice configuration. The idea is that we have a box with different particles moving with some interparticle distance L, which will introduce a scale in our problem, and with some momentum T, right? So we find useful to define this quotient, which is basically the ratio between the very famous de Broglie wavelength, which is basically h, the Planck constant over the momentum, over this interparticle means distance L. And the idea of this quotient is that basically it helps us to differentiate two different regimes for the study of the evolution of this system of n parts. If we have that the interparticle mean distance is small enough, we will end up into a quantum description of our system, for which we will need to know, for example, the wave function of this n interactive function, solve Schrödinger equation, and know the dynamics from a purely quantum theory, which is not a trivial task. Nevertheless, if this R is less or approximately equal to 1, a classical description of the fluid is actually allowed, in which basically what we will be solving is, or we will be applying, is the Ehrenfest theorem, that you know that it basically says that the dynamics of our theory will be uniquely determined by the initial condition. That is, if you know the position and the velocity or the momentum of the particles at some initial time, you will be able to know the dynamics afterwards by the Ehrenfest. Both approaches are really difficult if we have a very large quantity of particles. So sometimes it's also convenient to use a statistical description for our fluid, in which we know that the degree of freedom in this case will be the distribution function that basically tells us at any t and x in our space or in the domain in which the fluid exists, which is the probability of have a certainly number of particles moving within some range of velocity, and the dynamics of this will be given basically by the Boltzmann distribution, as you may know. Some other times it could happen that we have a ton of particles and we need to analyze a more complex system, and it's so large this end that could occupy some volume, okay, of length of side capital L, which introduces another scale now in our theory. That of course, since n is so large, this capital L will be much greater than this particle particle distance. So in this case, we can approximate this system as a continuum, and this is what I will understand by a fluid. In order to define this, we introduce now another parameter, because we have another scale in this case, which is the size of the box, which is a quotient between the distance of the particles and the size of the box. If this scale is much less than 1, we can think that this continuum will be composed by small pieces which are large enough to contain many elementary particles inside, right? But also small enough in order to guarantee the homogeneity, right? I cannot consider like my fluid element will be so large because I am basically breaking the homogeneity of the continuity that I would expect this fluid to have. I think that this is very nicely resumed in this plot that I took from a very old book. that basically relates some imaginary quantity. In this case, it's a measured density, but could be temperature, could be pressure, as a function of the volume, right, in which your instrument responds. The instrument with you are measuring this quantity response. So if your instrument is accurate enough that you can have information of the system at very, very small volume, what you will measure is basically a lot of oscillations around some equilibrium value for the quantity you are measuring. And nevertheless, if of course you start to lose accuracy in your instrument, what you basically will measure is this average that could also vary between some, because of some spatial distribution or some local facts. But basically what you have here is the average of this quantum fluctuation that could be happen at the microscopic level. So what about dynamics? So how we can mathematically describe the fluid? Well, we will say that the state of the fluid will be determined by basically by giving three fields, which is the velocity field, which is well described. You just think on a Newtonian theory how to define the velocity. The particle number density, which basically counts how many particles you have per unit volume, and some other thermodynamic quantity that will help to give or to have a knowledge of thermodynamic properties of our fluid. Could be the temperature, could be the pressure, the energy density, or any thermodynamic quantity you choose in order to describe your system. So these fields will satisfy what we call the hydrodynamics laws, but the hydrodynamics laws are not more than conservation laws that follows from Newton theory, for example. Conservation of mass, conservation of momentum, or conservation of energy. For example, the particle number conservation will basically follow the so-called, the very well-known continuity equation that I'm writing here, which is a conservation law that basically says that in some interval of time, the variation of the number of particles inside some volume is basically given by the flux of particles across this time-like boundary defined by the time that in which we are measuring this variation and the boundary of our domain. So this is just an example of what I understand by a conservation law, right? How to measure the variation of any quantity. In this case, it's just the particle number density, but you can also use it for the energy density or the momentum. Okay, so let us move now beyond and try to see how can we generalize these concepts we have just hand waving until now into the framework of general relativity. So we know that in general relativity, we have a very clear program on how to model matter and energy, because we know that all the information of the matter and energy will be codified in a symmetric tensor field, which is called the energy momentum tensor field. For an ideal fluid, which is basically, by definition, an isotropic fluid, which does not dissipate any kind of energy, and no transport phenomena are involved. So it's the very basic, most basic fluid you can have. It's easy to see that the energy momentum tensor for an ideal fluid will be given by this expression. This UA here is the force velocity of the fluid measured by some inertial observer at some point of space-time. This is the background metric, and rho and p are correspondingly the energy density and the pressure of the fluid. Of course, rho and p are also measured with respect to the same observer that is basically looking at the fluid moving with some force velocity u. So the continuity equation, for example, that I mentioned before, in this case, basically goes to the conservation of a new current, which is this particle number flux, that together with the conservation of the energy momentum tensor, which is the covariant way to write our conservation equations I mentioned before, we get to this system for the ideal fluid, which is the conservation of the particle number density and the conservation of the energy momentum tensor. So this is a coupled system of differential equations. You know that both n and t can be written as a function of for velocity. So basically, you get evolution equation for your velocity field and for some thermodynamic quantity here. We are also assuming that we have some prescription on how to relate the energy density and the pressure via some, for example, equation of states. Are becoming very famous now in order to model neutron stars, for example, which relativistic hydrodynamics is really useful. So one of the properties we need to be careful when trying to put this set of equations, for example, in the computer, is the notion of well-posedness. I will now talk a bit about that, but let me just say here that this system of equations for an ideal fluid system is well-posed if and only if the derivative of p with respect to rho is positive. So you can think that this has some physical meaning, which is reasonable, but basically this says that you have to choose from every relation you can find between rho and p via the equation of state. You just have to choose those equation of states that preserve this condition. If you have this, and you put this in your system for an ideal fluid, you will have a well-posed system. So let me review and give a detour on what I understand. What is well-posed? What does it mean? So this condition, well, dates back to the earliest, probably 19 and 20. I'm sure that you have heard a lot about well-posedness, so the idea is not to go through the details. Unless you ask me questions, feel free to ask any question, which does not imply that I will be able to answer them, but you can ask. I'm happy to receive a question. So this condition basically means the following. So a system of equation is well-posed if it admits a solution, so if the solution exists. This solution is unique if you prescribe the initial data. For each initial data, you have only a unique evolution, which is nice, because for a theory, a thing we want, and the reason we want to have a good theory is the predictability power of the system. You want to know what will happen afterwards. So this uniqueness condition is very important, but it's not sufficient. It's not enough. You need another condition that is within the idea of well-posedness that says that it depends continuously with the initial data. What does it mean physically? If you have an initial data and you let the system evolve, you will get some evolution. But what happens if you perturb your initial data just by a small quantity? What would you expect for your evolution? Well, if the initial conditions are modified just a bit, I would expect that my evolution for any further time will just change for a bit. So that basically means that you should be able to control your evolution, a norm, some mathematical way you can choose for controls your evolution with the initial data. So the mathematical way to condense these ideas that date back to 20s is basically given by this inequality. That says that if you have an initial data, and this initial data is a function that lives in some function space, you can bound the evolution at any time close to zero. This is important because this is a local well-posed. This is not a global result. It's just local in time. You can bound the norm of the evolution by the norm of the initial data. That could, if you see this inequality, you could say, okay, but this is too restrictive, because if the initial data has a very little norm, like the norm is close to zero, I basically don't have evolution, because I basically want to bound something with zero, which has no sense. But the point here is that we are allowing, this is a common misunderstanding in the notion of well-posed, that we are allowing this solution to grow time. It's not that the solution cannot grow, because say, okay, this solution grows exponentially in time, for example, the system is ill-posed because I won't be able to bound my solution with the initial data. And this is not true, because you are allowing this this factor here that depends on t, which is an exponential. So you can allow your solution, even for a well-posed system, to grow, which seems to be trivial, but it's a bit tricky. This condition is nevertheless super non-trivial because these constants k and alpha, which are real, does not depend on time and does not depend on any frequency, excitation, or nothing related to the solution. They only depend on the initial data, but not on time, for example. So that means that this should hold for any t, capital T, close to 0. So this is very non-trivial at this point. The problem is how to assess the hyperbolicity, the well-posedness of a theory, because you need to know norms, you need to some skills or tools of functional analysis, and probably it's not easy or not super interesting to start bounding and using all the Helder inequalities and all things that math people does. Fortunately, there are some ways to assess the well-posedness of the theory through another concept, which is called the hyperbolicity. So the hyperbolicity basically is that you basically forget about functional analysis that you need in order to choose the norm in which your solution lives, and give instead of that, you basically put some algebraic condition of your system of equations. So say that you can write these equations that I wrote here, you can just decompose it in a 3+1, for example, decomposition, and you get this system of equations here, which is quasi-linear. That means that this matrix A could depend on U. Imagine that U is now just a vector or a collection of your dynamical fields, and this A is basically the coefficient that multiply the spatial derivative here. I'm using the Einstein notation here. This is time derivative, and this is just spatial derivative, equal to some sort. So we will say that this system is strongly hyperbolic, right? It's a new condition if basically these A's are diagonalizable with real eigenvalues. If you take any set of numbers ki and you construct this new matrix here, if you manage to show that for any k, this element here is that this matrix here actually is diagonalizable with real eigenvalue, that means that your system is strongly hyperbolic, and that means that your system of equation is well-posed. So you will be able to put it in the computer without having to deal with the well-posedness or with some instabilities or some problem that may appear if you are trying to evolve a system that you are not sure if it is well-posed.
Sorry, but you're assuming that your well-posedness is global well-posedness, which is not.
No, not necessarily.
When you say that k and alpha do not depend on time, you're basically saying that at most the solution grows exponentially.
Yes.
It will not blow up. And it shouldn't be
well, a priori, this t that I'm putting here is close enough to 0. So it's not that for any t in your domain.
More later globally.
It's not global. Yes. A priori, it's not a global condition. You may end up with a system with but in general, no. And also in numerical relativity happens that you have a well-posed formulation for the Einstein equation, for example, not forget about the ADM, and you let it evolve for a long time, you will have some problem probably part of the time. So these results are, these theory questions are local. This one dates back to Hadamard. I think Hadamard was the first pioneer or seminal work on this idea of well-posedness. But then there were a lot of works by Friedrich, by Schoke-Bruhat in general relativity, by Robert Gerock in general classical field theory. It's a boundary between physics and also mathematical relativity. And well, for example, David Hilditch, which is here, he's an expert on these topics. And well, there are a lot of things to do, but it dates back at least as far as I know to the early 20s by half. Okay. Until now, I have talked about what happens with the hyperbolicity of the equation of fluids, which are just the ideal fluids. So what happens if we move and we try to include dissipative effects in our fluid? Remember that now we have a framework, so probably the physics will be a bit hidden at the beginning, but we will try them to just come up at the end. The framework is basically that we have the for velocity of our fluid, the particle number, density, and some thermodynamic quantity that you can choose. For example, the pressure or the temperature. So in order to extend this scheme for non-relativistic fluids, the idea is to perturb or to add some contribution to our energy momentum tensor. This is the ideal energy momentum tensor. You add some piece up to some order in a way that appears some new effects on your field. So the natural way to generalize this is to allow our energy momentum tensor to contain, for example, derivatives of our velocity or derivative of our thermodynamic. The first thing you could do. Even more, if you assume the laws of thermodynamics, you can get a closed expression for this candidate of contribution to the energy momentum tensor in terms of some quantities that basically are related with the gradients of your for velocity in this case. So in this case, remember that this pi here should be symmetric. So basically the unique terms we can add in this contribution are the shear of our velocity field and the expansion, which I'm basically trying to show here. The shear is how the different layers dissipate when one moving on top of the other, and the expansion is basically how is the divergence of the velocity field. So the problem with this, so imagine that we could model at some point, we can get some heat equation, or we can define some. I will do it furthermore in this talk. But imagine that we now assume that we have a new energy momentum tensor, and we want to impose our evolution equation, our conservation equation to this system. We will have a problem. And the problem is not mostly related with the well-posedness, but it's related with another important quantity, which is property, which is called the causality. So imagine that you take this energy momentum tensor with the perturbation we put, and with the contribution we put to the ideal fluid, and we perturb a bit our dynamical fluid. I choose in this case the rho and the for velocity. If you put this perturbation in the evolution equation and you only work up to first order in this delta, you will end up with an equation. This is one of the equations that you get, because it's, for example, I put just an example, the y component of the for velocity. You will get an equation of this type. I imagine that you can probably recognize this equation of first order in time and second order in space. So this is the heat equation, basically, approximately. The heat equation is well posed, so it has a unique initial value problem, a unique solution for given a unique initial data. So it's not hyperbolic; it is parabolic actually, but it's well posed, right? The problem with this equation is that the modes can propagate with infinite speed. One way in which you can see this is, for example, choosing an ansatz, which is basically a wave with some frequency, some wave vector k and some frequency omega. You put this ansatz in the equation and you get the following dispersion relation. You know that the velocity is basically take the derivative of omega with respect to k, and this is linear in k. Unlike, for example, the wave equation, which you get omega squared equal to k squared, because you have second derivative in time in the wave equation. So here you have a linear row, and for high frequency modes, the velocity of those modes is infinite. So basically you lose very appreciated property we want, any phenomenon we want to analyze, which is the causality. Of course, this does not mean that the heat equation is wrong, but if we want to put this in a context of general relativity, and we want to manage for a theory for general relativity, we want like to deal with this kind of equation. A very similar problem occurs, for example, when trying to generalize the usual heat equation, or the usual equation for the heat flux in general relativity. So there is a very nice paper. I won't have time here to introduce it, but it's a very nice paper by Oscar Reula and Ana Laura Garcia Perciante, in which they managed to hyperbolize the heat equation in a way which is consistent with general relativity. So if you are interested on this work, I can then give you the reference. So we have this problem with this theory, this attempt to model dissipative fluids. And this is, well, this is problematic. So basically you say, well, what else we can do? Probably considering an expansion with higher order derivative terms, or no. Or probably we have to change mind and try to manage any other way to model an energy momentum tensor at first order, for example, in derivative, that gives a causal, stable, and well-posed. As you can see, this is a very long problem that dates back from Eckhart and Landau-Lifshitz, 40s and the 50s. Basically, they deal with first-order theories, and at least they couldn't get a well-posed, stable, and causal theory just with first-order terms, with first-order gradients of the dynamical value. Then it came up this Israel-Stewart approach, in which basically they managed to have a well-posed, stable, and causal theory, but it's a bit tricky the way in which they solve the problem, because they basically add terms of second order in the expansion of gradients that if you want to know, or if you ask about, for example, the phenomenology, the relation, I mean, with the phenomenological relation of the coefficients that are multiplying these second order terms, is a bit tricky and not from first principle a priori. So, but it's very famous, and people usually use Israel-Stewart, for example, if you want to consider some dissipation in the matter you are involved. Afterwards, there came some more modern approaches, due first to Liu, Ruggeri, Lindblom, and Penissi, which they analyze this type called divergent type theories. I will talk a bit at the end of my talk about what we managed to do with Oscar Reula during my PhD regarding these divergent type theories. The idea is that you have a generating function, like in thermodynamics. You remember that you have one potential that basically have all the information of your thermodynamical system. Well, this idea can also be applied for some set of concepts of fluid equations. These ideas then were further deeply studied by Gerov and Lindblom, and basically they took this idea and analyzed the initial value problem and get some conditions this generating function should satisfy in order for the system to be well posed, for example, causal. About the divergent type theory. Yes, in Cordoba. Yes, you said, yes, in the GR conference in 92. I think it was in Huerta Grande, in the hills.
Wow.
Yes, no, but it's super nice because
I remember him talking about that.
okay, I grew up in Huerta Grande, so it's I know I in the 92 I just had 1 year, so of course I didn't attend the conference, unfortunately. Well, thank you for letting me remember that. Okay, so as I said, the very first attempts for dissipative fluid theories was date back to the 40s by Eckhart and Landau-Lifshitz. I imagine that you are familiar with the book of Landau, well, series of books of Landau-Lifshitz, in particular the one about continuum media. Well, there is a chapter in which they present I will write a chapter about relativistic fluid dynamics. Well, it's the very first attempt of Landau-Lifshitz in the 60s, probably the second one, that tried to model dissipative fluids in general. So it's a chapter which is not a review, it's very, very new and important fact. After this very first series, I think there are 3 or 4 works about Eckhart on that. The problem of this first attempts of fluids dissipation, or fluid theory candidates, were realized by Hiscock and Lindblom in the 85, that basically they in this very, very nice paper, they generalize these theories that took Eckhart and Landau-Lifshitz, the more general setup. And they found generic instabilities similar to the one I showed you before with this example with the perturbation of the heat-like equation, reporting some generic instability. So basically, the idea is the following, and I will call this first order theory round one. What is the general idea? So basically, they took a time-like vector field, which is basically for velocity of the fluid, and you write the most general symmetric second rank tensor field you can write by terms only of u, right? So the most general one you can write is this one. You have a part which is totally parallel to you, a part that is part parallel and part perpendicular to you. So I'm introducing this q vector field here, which is orthogonal to you, so it will be space-like physical view. This H is the induced metric, which is not necessary an induced metric because this U could not be hypersurface orthogonal. So I would say that it's a projector to the space orthogonal to U. And this part, which is the stress part, which is totally perpendicular to U. For the particle number, they also add a term here. Remember that without this mu, you get the perfect fluid one, right? And if you, of course, turn off this Q tau, which is the trace of tau AB, and tau AB, you put it to 0, you get, of course, the energy momentum tensor of the ideal. So this nu is also perpendicular to you, and this is the most general tensor and vector you can write in this form, given for a given for velocity, given vector. They also assume the existence. I didn't talk about the entropy, but of course, in a fluid theory, you need to define an entropy regarding the second law of thermodynamics. This entropy current in this covariant framework, which should satisfy that the divergence is at least 0 in the perfect fluid case, or greater or equal than 0. The most general entropy current you can write up to first order. I mean, the most general entropy current you can write with these elements you have here is this one. And if you take this entropy here and you take the divergence, you will end up with a very long expression. Hitchcock and Lindblom say, okay, some natural way to enforce this inequality to hold is basically to choose the following relationship between derivatives of our velocity field and these new fields that I am putting. These are called the constitutive relations, because in the fluid scheme, you only have your evolution equations, and I am adding here new fields. So if I am adding here new fields, I should be able to write or to prescribe these new quantities here as a function of our thermodynamical variables, which was, for example, the temperature or the pressure, the particle number density, and the velocity field. Right? I cannot just add new functions. Yes. The justification of that, well, I quoted this very good question. I quoted this natural here because basically what happens is that when you compute the diversion of this vector field here, you get terms that go, for example, as tau AV. You have to also to use, this is on shell, right? You have to use the evolution equation. This thing.
I mean, the expression for now, that's
the second law of thermodynamics, that if you have the, say again?
It's a closed system.
Yes, if it is a closed system, we are assuming that this is in a closed one. But yes, you are assuming the same thing you assume with the second law of thermodynamics, which is the existence of 2010. Okay.
Well,
yes. So believe me that basically they prescribe these quantities here as relating, for example, the tau AV, which is the stress part, which will be proportional to the shear, which is something that we use. This Q will be the heat equation. You can recognize here that it's minus the gradient of the temperature. So it sounds to be a heat equation. And this nu, basically a diversion of the expansion. But the problem is that you perturb the evolution equation using this constitutive equation, and you put this here, you get this Hitchcock and Lindblom instabilities, because they found some modes. I think it was some transverse or longitudinal modes that grow without bound. So again, the question is, we have to say bye-bye to first order theories, or we can do something else. So now it comes up another approach, which is a very modern approach that I would like to discuss here, which is this Benfica, Wisconsin, Oroña, and Coptum approach for studying first order theories. They're being very famous now because there are groups, for example, groups of Franz Pretorius or Pau Figueras are evolving these equations. And it is nice. I mean, it's very nice. But I think that there are some issues regarding the initial value problem that should be discussed a bit. So let me just briefly introduce that. So again, in this BDNK approach, we have exactly the same quantity of degrees of freedom I put before. This mu is the chemical potential, that is the conjugate variables of the particle density, so it's the same. Our velocity and, for example, the temperature. I wrote again slightly different from before. The most general T and N you can put here. Notice that now this E, P, N are scalar fields. This Q and J are vector fields orthogonal to U, and this P is, as before, transverse to U, but now it's also symmetric, well, symmetric of course, and also traceless. So I'm basically absorbing the trace I put before in this new pi and putting it. All of this is general. If you have a time-like vector field, you can always, because the unique thing you have here is a time-like vector, the velocity of your field. All the rest is just linear algebra. I'm not doing anymore. So when does hydrodynamic join in shell? I put here. Well, if you associate this time-like vector field with the for velocity of the fluid, for example, you can ask to be normalized to -1. And the second very important point is to express these abstract quantities I put in red as function of our thermodynamic variables. If you manage to do this, you have a thermodynamic theory, which is okay. So the question is how to prescribe these quantities that I am putting here in terms of our thermodynamic variables. Well, you can think that, for example, these EPN are basically scalar fields. So which scalars, how many scalars you can construct with the hydrodynamic variables you have here? Okay, I can put T, I can put mu, and what else? Well, the norm of B, I put, which is basically the diversion of order. And then you can, for example, consider the in this case is -1, but you can consider the diversion. Then it starts to count derivative of our norm. So without derivative, you only can have T and mu. With first order derivative, this term, and then second order derivatives, and then third order derivative scalar. This is the most general scalar you can build up with these quantities and their derivatives. The same with the vector, Q and J. Again, this is a more abstract notion of constitutive relation. We want this expression of our red variables I wrote before in terms of our T, mu, and D and their derivatives, right? The way to fix them is, again, the most clean way to do this is throughout a gradient expansion, considering terms that are zeroth ordering derivative, then terms which are first ordering derivative, and so on. The unique assumption we need to have here is that the order of magnitude of the zeros of the term, for example, the fields in equilibrium will be larger than the ones that are account with first order derivatives, and so on. So, for example, for ideal hydrodynamics, you don't want derivative of your thermodynamic field to appear, so that gives the trivial constitutive relation that heat flux, J, and stress are basically zero. For dissipative hydrodynamics, well, this is the question: how to fix these quantities in terms of this gradient expansion I put before? And the reason is that you can do it. You can choose the way to do it because there are no notions, for example, of temperature out of equilibrium. The unique notion we have, thermodynamic of temperature, is in equilibrium. And these systems are supposed to be out of equilibrium, but not a lot, just a bit. So you can perturb or let the system to have different form as long as they coincide when getting back to equilibrium. I'm just resuming this here. So this epsilon, P, and N in blue are the quantities in equilibrium. And basically you are adding some contribution, in this case, first order in derivative. This is why I'm calling it first order. If you read the paper, you will say this idea of choosing a frame, which you can think, okay, but the frame, what is a frame? coordinate system, which is an observer. Well, in this context, a frame is basically the way you fix this deviation from equilibrium for the variables that are accompanying your TA. This is okay, as I show you, as I explained you before. There are no definitions of temperature out of equilibrium, for example. So the idea is to vary these quantities T, mu, and U, and compute the variation that we will get given this prescription here, and see if the new system of equation is well posed or not. Just as an example, let me mention this work by Benfica, in which they prove, or they managed to prove, this local existence and uniqueness in solid spaces, like the full well-posedness result, for conformal fluid. Conformal fluid is basically ultra-relativistic fluids. I will mention this some in the end. I hope I will have time. They basically start from the most general energy momentum tensor. The thing that the fluid is conformal ultra-relativistic is hidden in the equation in the radiation equation of state they use. The energy density is proportional to the temperature to the 4, which is equivalent to say that the energy density is basically 3 times the pressure. And they prescribe, because of that they choose for probably some stability and causality argument, the following constitutive relations for these 3 fields that you could use. So basically, the evolution equation they get is only the conservation of the energy momentum tensor. They are not assuming particle number conservation. So you have here, as you can count, 4 equations, which are second order in U because you have gradients here. So these are 4 second order equations. So you have 4 equations. But if you want to think in a first order theory, you will end up with 8 dynamical or physical degrees of freedom. If you want to think that they satisfy first order equation, is common in physics. So you have 8 equations of first order here. The problem is that when they try to prove the hyperbolicity of this simple set of 4 evolution equations, they enlarge the system in this way. I can explain in detail, not now, but I can explain in detail how do they get the system of equation. I could also do it. It just took me some days, but you can do it. It's not difficult. The problem is that you get a 30 by 30 system. So you start with a system with was 8 first order equation, and you end up with a system of 30 by 30 first order equation. This is the principal part because it contains derivatives, first order derivative power fields, and these are just functions of the dynamical variable, which are these ones, which are terms. So for example, here you don't have constraints. You manage to write your system of equation without any constraint. So what they did is basically how they did this. Well, they introduced these variables here, which are of course gradients. If you want to manage a first order system of equation, you need to define new variables. So basically they define this S, which is the acceleration of the fluid, and this SAB, which is basically the Strandberg part of the gradient of the fluid. So they use this, but the problem is that, look at this. U is a dynamical field because it satisfies, this is the evolution equation for U. And S is also a dynamical field. The evolution equation is here. Well, for example, with this example is here, with S is here. So you have one evolution equation for U here. You have one evolution equation for S here, but you have a constraint, which basically is this equality, which is just a change of variable, you can think, should be propagated along evolution because you have evolution equation for both U and S. So that comes our problem that we are now working with Aaron Kovacs, also from SISSA, and Fernando Ábalos, which just joined Carlos Valenzuela in Mallorca. We are studying this hidden constraint propagation that is not present in their paper. I have nothing against with Benfica. I'm happy to find a first order formulation which is well posed because you don't have to move to second order. they have 30 equations of motion, but physically we have 8. So we expect 22 constraints equations, right? 22 plus 8 is 30, that they are not mentioning in their work. What they do in the work, which is a very nice work, and it was published in Communication, so it was an important paper, is take the system and show that the principal part is diagonally stable with real eigenvalues and a complete set of eigenvectors, which is okay. The calculation is okay. But we think, but at least it's probably I'm wrong, but we think with Aaron and Fernando that this is not enough because there are hidden constraints, 22 constraints that are not explicit in the paper. So the first step we did is to figure out which are the constraints. Well, of course, the constraints are three. The fact that the for velocity has norm -1. This basically the acceleration. If the for velocity has norm -1, the for velocity should be perpendicular to the acceleration. This is very easy to see. And of course, the other constraints are basically their definitions of S and SA. The idea is to construct a system of evolution of these constraints, because the constraints have to be 0. If you choose an initial data that the constraints are 0, right, they should propagate along evolution. We are working on trying to find this first order system for the constraint. We need this to be homogeneous because we want, of course, the unique solution we want is the trivial solution for the constraint, C equal to 0. So we cannot put any source, for example. If this system, once we have this system, is well posed, that means that if you initially choose initial data such that the constraints are already satisfied, because of this nice result here we are trying to show, this constraint will be propagating a long time, and I will be really happy with Benfica theory, right? With Benfica theory. But we think that it's not necessarily happy. We don't have any intuition about it should be trivial because, no, you have to just sit, write the system using the evolution equations, and manage to prove that the system is well posed or strongly hyperbolic. This is an open problem. The first time I'm talking about this with an audience, so if you have any ideas or something, just let me know. But this is a work in progress with Aaron Kovacs and Fernando. If we cannot find the system, or if we find the system and we see that the system is not hyperbolic, that means that some of the constraints won't propagate correctly, right? And if that happens, we would like to see it numerically. So this part also has a numerical counterpart. It would be very nice work for some students. Okay, so I think I'm done with these first order theories, and we are on time. We had some questions. We had before some questions. So just let me mention in 1 minute, what I did during my PhD. During my PhD, Benfica theory didn't exist. So we were convinced that first order theories for dissipative fluids were not a good idea. So we went to second order theory, and we took this Gerock and Lindblom theory that he was mentioning before. Basically, the evolution equations are the same as the ideal fluid, and you add another equation ad hoc, which is basically some sort of constitutive equation. We also allow the existence or require the existence of an entropy in the same way as before. And the idea is that this set of equations with these dynamical variables can be nicely rewritten in terms of a set of abstract variables, right? And because of the symmetry of the energy momentum tensor, you can prove, this is a work done by Gerock and Lindblom, and Penisi and Ruggeri and Liu, that basically they show that the existence of this generating function, which is a scalar field that depends on a set of new variables, such that if you take derivatives of this scalar field, you get the physical quantities that we had before. Well, then you can write the entropy current some way, and all the dissipative degrees of freedom of the theory and basically encode in this tensor field. So this chi should be some sort of conjugate variable with a particle number. This chi here, this covector here, should be basically the for velocity of the fluid. And this chi here, which is traceless, is basically the diversion of that. Well, I think I explained something about conformal fluid. So if you have some question, we can discuss afterwards. But basically, we ask our theory to be conformal invariant. If we rescale the metric, we want our equation to become the same. This gives some restrictions to our fields. The most famous one is that the energy momentum has to be traceless. But now we have this A equation, and well, you have this condition. What we did in our PhD and also in collaboration with Luis was to find the unique generating function for these conformal fluid theories. We have here the theorem for well-posedness about this second order theory. Well, then we have the typical numerical implementation. If we use the abstract variables I introduced before, we get a very nice system, but it's not of conservation form. So we cannot capture shocks, for example, which in fluids is fundamental. So we have to move to this conservative formulation, which is in terms of the primitive variables, the conservative variables, and try to find the relation numerically, because they are highly nonlinear, between the fluxes and our abstract values. Well, and then we have some nice results. We don't have time to. We basically explore how the evolution changes and comparing the evolution with respect to the ideal fluid when changing the different parameters of our theory. This is work done by Pablo Monte, which is Oscar Reula's PhD student. It's not my simulation, but we are collaborating. We also model the source that appeared in the equation of phase in a very nice way. This is the most general source that is weight balanced because of the conformal invariance. And basically we see, okay, how the system changes or how the dissipative quantities now that appears because of the dissipative fluid deviate from zero, which is the case in the ideal case, in the Euler equation for the ideal fluid case, moving the different constants. So I would like just to show, for example, that the nu doesn't change, but this tau, which is the unique component we are evolving of the stress part of the energy momentum tensor, start to play an important role. This is basically the energy density. The black one is the Euler case, and the other ones are the dissipative case, turning on this source. And I think this is basically what Pablo has been done during this time, which was really complicated problem. We wanted to have this ready before, but there always appear some problems in the numerics, so we could fix it now. Okay, so as final remarks, we know that we need theories, dissipative fluid theories, in order to, for example, model compact objects. We have the symmetric hyperbolic theory for simulating the conformal fluids. The abstract variables helps for the symmetric for the hyperbolicity of the theory, but not for the numerical implementation, because we have to move back to the conservative scheme. As future perspective in some short terms, well, we have to publish these results with Pablo and Oscar. We need to finish this constraint propagation with Aaron and Fernando. And the idea is to use this one-dimensional code, which is very simple, to just test the Riemann problem or turbulence effects for dissipative conformal fluid. And of course, to generalize these techniques for more general diversified theories. For the long-term point of view, of course, we would like to have the full code of this whole program we developed for the diversified theory that I unfortunately didn't have time to explain. I thought the first part would be shorter, sorry. Also with Enrico Barause at SISSA, we were wondering on modeling anisotropic fluid as well. Remember that an ideal fluid is by definition isotropic. So you can also think that anisotropy is also a way to dissipative or to move beyond an ideal fluid, not necessarily with heat propagation. And the last question that is interesting to me is regarding the fluid gravity correspondence. You know that it's a very nice fluid gravity correspondence. So that relates some black hole solution in asymptotically ADS in a bulk of dimension D, for example, with some conformal theory in the boundary. I'm not an expert on that, but you can put a conformal fluid there. And if this conformal fluid is totally determined by one generating function, that means that the gravity inside should also be determined a priori for just one function again. So the idea is that would we be able to find some generating function, but for gravity and this in this case, this is a very open question, probably have no too much sense, but at least for me it was interesting. Okay, so I think I'm done. And thank you. Sorry for the time.
Yeah, it's already time. I mean, we should already be finishing by now. Maybe if you want to ask one or two very quick questions.
Yes.
So I think, for example, Pretorius has tried to evolve this PED in cases
Yes.
of harmony. And you were wondering about the constraints and your difficulty, but can't you check if the numerical difference propagate the constraint?
I think that the thing is that the short answer of that is that Pretorius is not evolving the 30 by 30 large system I showed. They managed to do it. They evolved the fourth equation of second order, basically the velocity and the pressure, or the which is okay, because now that you have the prescription of the energy momentum tensor, you can do it. Both schemes are the same. So they don't have any constraint, so they don't have to preoccupy about the constraint because they are not evolving this capital S. So they don't have they use the well-posed formulation, but for evolving other equations, and they don't have any problem. So this is probably result that favors the work by Benfica, which is okay. So, yeah.
So if I remember correctly, so the point is that one has to have this like first order reduction constraint, right? And then propagated.
Yes.
And this is because the hyperbolistic analysis is done in first order form.
Yes.
Could be a way to do the hyperbolistic analysis without introducing this reduction.
Yes. Yes. The hyperbolicity, I'm not totally sure. Of course, there exists results on well-posedness for higher order system of equation, but from the functional analysis point of view, so you have to not algebraic.
Maybe you should check a paper by it's like hyperbolicity sort of without having to do
Okay.
first order reduction.
Okay, for sure. Yeah, and also Aaron is working on hyperbolic, hyperbolicity of high order theories as well. So it would be. I'm sure that, for example, Aaron is aware about the papers. But yes, of course, please send me.
If you enjoyed the video, like and subscribe.